Good morning, ladies and gentlemen. Hope you're all sitting down nice and comfortably, ready to start taking notes. This video is on differentiation by first principles. I realise you've covered it in Year 11. We will go through it quickly as we can. Alright, first of all, what are we trying to do? Well, by differentiating a function, we can find the instantaneous slope at a point on the curve. This, in turn, gives us the instantaneous rate of change and helps us find turning points, maximums, minimums, etc. So, what does this look like? Well, here, you can see this red line is the true tangent to the curve at point P. This blue dashed line is an approximation. And the whole point of first principles is, as we drag this point closer and closer to point P, we can see that the blue dashed line gets closer and closer to approximating the true tangent. So really, we're looking at the limit of what happens as this point, Q, drags towards P. In slightly more algebraic terms, you'll have seen this diagram before, but it's worth having again, and it's the logic of it that's important. Once you understand the logic, the rest of first principles is just an algebra slog, and there's a fair bit of algebra to get through. Alright, the logic of this is, if we want to find the slope at point A, here, we want to find the slope of a line, so really we're looking for rise over run. This bit here is rise, this bit here is the run. Now, using function notation, f of x, we can see that the rise over run, rise is equal to this top line here, take the bottom line there. So that's the difference in the level, gives us rise over run. So it's f of x plus h, take f of x, over the run. Now the run is x plus h, take x. X plus h take x just leaves us with x. And what we are wanting to do is consider what this looks like as h gets really, really small. Did I say take x leaves us with h? H, there, on the bottom. We want to look at what happens when h gets really, really small. This here will disappear, and we'll start turning this AB line into the true tangent. So we say that we want to take the limit as h approaches 0 of this pair here. And that is what f dash x is equal to, or the differentiation of x, differentiation of the function x. Alright, there it is written out more neatly. My handwriting is atrocious. Apologies. Note that you'll also see f dash x written as dy on dx, depending on what sort of notation we're using. Alright, a couple of examples. Find from first principles the gradient of the function f of x where f of x is x squared, take 3x. Now, the whole purpose here is to be nice and systematic, and we're hunting for a common factor. I'll explain what I mean in a second. Limit as h approaches 0 of f of x plus h, take f of x on h. If I go too fast, pause me so you can take notes. If I'm going too slowly, then speed me up and I'll sound like a chipmunk. Alright, now, what we do here is we substitute in x plus h into this first one here. So limit as h approaches 0 of f of x plus h, and we substitute it in. So instead of x squared, it is x plus h squared, take 3 lots of x plus h, take f of x. Now f of x is just the original function, but this time we put it in brackets, and that's important, you'll see why in a sec. X squared take 3x over h. Now the reason we can't evaluate this straight away is because to evaluate it directly, we would really love to just let h equal 0. We can't do that because h is on the bottom, and we can't divide by 0. So we can't just let h go straight away to 0. We need to get rid of that h on the bottom first. And to do that, we start doing some algebraic manipulation. Alright, so on the top, expand and simplify. X squared plus 2xh plus h squared. That's the perfect squares expansion for the first portion. Take 3x, take 3h, expand that out. Now this is the important bit that people often forget, is that negative comes into both of those. So we have minus x squared plus 3x all over h. Now let's collect like terms. So we have a positive x squared and a negative x squared. We have a positive 3x and a negative 3x. And there are no other like terms that cancel out. So let's take that one step further. Limit as h approaches 0 is now going to be 2xh plus h squared take 3h over h. Now that's interesting because you notice how on every term on the top we have an h, which means there's a common factor of h, which is fantastic. So what we can do there is remove that common factor and write this as 2x plus h take 3 all over h. Now once we've removed it, we can cancel those common factors. And this means that we have limit as h approaches 0 of 2x plus h take 3. Now here we're not dividing by 0, so we can let the h disappear after 0, which means we can evaluate it as f dash x is equal to 2x take 3, which is exactly what we're after. And I know last year you were taught how to differentiate polynomials the quick way, not just first principles, so you should be able to look at that and say 2x take 3 is where we're going. And it's usually a good idea to have a good idea of where we're going to start with, particularly on ones that look a little more difficult like this. So let's say that this is our f of x and we want to differentiate it by first principles. First thing I would do is I would say, well, what does that really look like differentiated using the shortcut way? Now this here, note, is the same as minus 2x to the minus a half. And if we were then going to differentiate that using the rules of differentiating polynomials, we're going to drop this power out the front and then reduce the power by 1. If we reduce the power by 1, we have x to the minus 3 on 2, and minus a half times minus 2 is positive 1. So we know before we even start that that there is our endgame. One lot of x to the minus 3 on 2. That's where we're going. Now let's see how we go with the algebra to get there. And there's a few tricks that are worth watching here. Alright, so same start as before. I'll do it out here. Limit as h approaches 0. F of x plus h take f of x over h. Now note, if you're going to do it by first principles, you do have to show this working. The examiners expect you to show all the first principle steps, because we all know we can get there easily, but the point is showing how you get there. Alright, limit as h approaches 0, so we have limit 2 over minus 2 over square root of x plus h. Take minus 2 over square root of x all over h. Once again, we can't evaluate for h directly because it's divided by h, so we need to do something algebraic to manipulate a common factor of h out of the top so we can cancel it with h on the bottom. That looks hideous, so there's a couple of guiding principles I'd go for here. In general, on top, if you have square roots, get rid of them. If you have two fractions, make it into one fraction. Won't work every time, but that's generally what we're aiming for. Get rid of square roots, make into one fraction, and look for an opportunity to pull out a common factor of h. Alright, so to start off with, I'm going to get rid of the square roots. Square roots here, we can multiply by 1. Now, multiplying by 1 here is a cool trick in that 1 can look like lots of different things. So for our purposes, 1 is going to look like minus, apologies, let me start a little further up, minus 2 over root x plus h plus minus 2 over root x over minus 2 on root x plus h plus minus 2 over root x. Note here, those are the same and we're dividing them by each other, so therefore it's just 1. And what we're aiming to exploit here is the a plus b, a take b is equal to a squared take b squared feature. Difference in perfect squares. Alright, so how does that work looking over here? Well, we multiply the left-hand side here by 1, and what we get is, keeping the limit as h approaches 0, first terms are multiplied together, squared, so that's positive 4 over x plus h, because square root times square root disappears, which is lovely, minus 4 on x, and that is all over h times this bottom bit, minus 2 on root x plus h plus minus 2 on root x. Now, some of you are probably thinking, this h can be expanded in there. It can, and you're right, but we don't want to, because we want a common factor of h on the bottom, because eventually we're going to cancel it. So there's no point expanding it in, you're just going to have to factor it out eventually anyway. So leave it like that. Alright, so then we have limit h approaches 0. And we want to, ideally, write the pair of fractions on the top as one fraction. So let's look over here at how we would do that. 4 on x plus h take 4 on x. Now, some of you might be able to simplify that really comfortably. Others may struggle a little. What we're going to aim for is x plus h as a common factor on the bottom. The reason we're choosing that is because we can multiply both of them up to get there. And then to get from here to there, we multiplied by x. So we have to do this. What we do at the bottom, we have to do the same to the top. So that becomes 4x on the top. Similar logic here, this is take 4x plus h. And that there gives us a fraction with a common denominator, so we can write this as 4x take 4x plus h on x plus h. Right. So that is this pair of fractions here written as a single fraction. Yep. Ugly, but you will get similar ones to this. Now, let's simplify the top. Simplifying the top, we can imagine this 4 expanding out to have a minus 4x and a minus 4h. Note here that we have 4x take 4x is 0, so then we're left with minus 4h on top. So limit as h approaches 0 is minus 4h over x plus h over this entire mess, h minus 2 on root x plus h plus minus 2 on root x. Alright, what's cool is here, that h is a factor of the top, because you can think about this as minus 4 on x plus h times by h. So it can be taken out as a factor. Therefore, if it can be taken as a factor, it can be cancelled with the h on the bottom. They go. And what we're left with is minus 4 over x plus h over minus 2 square root of x plus h plus minus 2 root x. Right. Here, note that we're no longer dividing by h. So because we're no longer dividing by h, or h is no longer a factor on the bottom, we can evaluate this directly. So if we're going to evaluate this directly, we basically let all the h's go to 0. And if we let all the h's go to 0, we can replace limit of f with f dash x. What we get is minus 4 over. Now that h there goes to 0, so this then reads as x squared over minus 2 on root x, because the first h disappeared, plus minus 2 on root x. Alright, now that is the differentiation. And it looks nothing like what we're aiming for, so we have a bit of algebra to fix it up. Fixing it up looks a bit like this. Minus 4 on x squared over minus 4 on root x. I hope you're happy that these two are common denominators, so we can just add the top, giving us that. Now here we have minus 4 on x squared divided by minus 4 on root x. Now for those of you who remember fractions work, you can keep, change, flip. Keep the first fraction, change this to a multiply, and flip the second one. Which is pretty cool, because here, minus 4 and minus 4 go, and what we're left with is root x on x squared. Root x on x squared, if we take a root x or an x to the power of a half out of both, is just 1 on x to the 3 on 2, which is x to the negative 3 on 2, which is our final answer. Alright, that was epic, but you're in your 12 methods. It's going to happen eventually. So, hopefully that helps you with the homework sheet that I know you have, and should help you in class as well. Can you check your understanding by doing these? Use first principles to find dy dx of that. Then, use first principles, differentiate that, hence find when the tangent equals 0. So you'll need to solve a quadratic at the end there. Thank you for watching the full 15 minutes. I promise they won't always be this long. But first principles just takes algebra. Enjoy. I'll see you tomorrow in class.